Is it just me, or is seeing how engines work truly magical? Like, how is this design even conceived? The fact to turn heat into something movable. Well, today, I'm gonna take you on a journey rediscovering fundamental truths behind gases, how they can do work and transfer energy between two objects, and then analyzing a unique engine cycle. Imagine you're a physicist in the 19th century, and that you're experimenting with different gases. Your understanding of gases is that they're made up of a number of particles, all colliding with each other and different surfaces, to produce different results. You realize that if you put gas in a sealed container, like a piston, some interesting properties arise. For one, it takes some force to compress it, which is unusual because to the naked eye, the container is empty. Scientists around your time call this property of the gas exerting a force over the surface area of the container pressure. The only reason that this force doesn't move the piston is that the pressure from the air above it cancels it out, keeping the piston at rest. You also try changing the temperature of the gas by heating it. Heating the gas inadvertently changes the volume. Specifically, if the gas is hotter, it starts pushing the piston up to equalize the pressure with the surrounding air. And also, you realize that changing the temperature of the gas changes the amount of force needed to compress it. Specifically, hotter gases require more force to compress. But these three relationships are not exactly new to you, because your other science friends already discovered and published them. Just on a quick side note here, although these three laws make sense, that doesn't always mean that they're true in real life. Just because I constructed arguments to make them seem like they should be true, doesn't mean that they are actually true. So, I recommend doing some labs at Pivot Interactives, that website is a gem, to empirically prove some of these, especially Boyles' law, which is really annoying to think of an experiment for, which the people at Pivot thought of geniusly. I also recommend checking out some of the PhET simulations, which I've linked below. Now, anyways, back to the video. However, if we combine them together, we get one single equation. First, let's try to dissect what this equation is saying. Replacing the proportionality sign with a proportionality constant instead, we can see that pressure and volume are both directly proportional to temperature, and inversely proportional to each other. If we rewrite the equation, we get that pressure times volume divided by temperature, in any state for the same substance, will always be the same number, a constant. The reason this equation is so useful is because if we know the first two values, we can automatically figure out the third one, if we know what this constant is. So before we get into the nitty-gritty of the actual ideal gas equation, here's a practice problem that you can try out. Okay, now for the actual ideal gas equation. So to get the actual ideal gas equation from what we have, we only need to figure out a few things, specifically the factors that can influence the value of K, the constant. So what did we keep constant when we made this equation? For one, we kept the type of gas constant. But what does this really mean? Well, the only property that differs between different gases is the mass of each particle. But changing the mass of each particle doesn't affect our value of K. To see why, well, it's important to look at both pressure and temperature, because they both depend on mass, and since one is in the numerator and another in the denominator, they both cancel out, and therefore mass can't affect the value of K. Well, another factor that was kept constant is the number of particles. It's pretty easy to see that the number of particles is proportional to the volume, which is called Avogadro's law. So it should be on the right-hand side of the equation. And now we just need another proportionality constant, which will actually stay constant between different types of gases. And let's call this R. Now, nothing else can affect this value of R except a change of units. So let's do that now. Instead of n being the number of particles, let's make it the number of moles of particles. So we don't have to write a number in the billions or trillions each time we perform this equation. For anyone who doesn't know what a mole is, it's just a huge number used for convenience. Now we can find R empirically by plugging in values for pressure, volume, and temperature, and the number of particles. This constant turns out to be 8.314 pascals meters cubed divided by Kelvin moles. And now we have our ideal gas equation. So, are we done? Well, this equation only turns out to be an approximation, albeit a very good one for the actual non-ideal gas law, which looks something like this. I won't go into much depth about it, but this part corrects for the intermolecular attractions between the particles in a gas, and this part corrects for the total volume minus the space that the individual particles take up. However, we don't really need to use this because the ideal gas law is a really good approximation. But although this equation is pretty useful and pretty accurate, it tells us nothing about how we can convert heat energy into something that does work. So what do we know about energy? Well, first, we know that energy is always conserved in a closed system. So where does energy from heating the gas go? First, let's call the energy that we get from this heating Q, out of convention. Note that if a gas is cooled, Q is negative. Well, some of the heat energy does work on the piston, moving it up and down, acting a force on it for a certain distance. But some of the heat energy goes into changing the temperature, which is a measure of the average kinetic energy of the substance. So let's try to quantify how much heat goes into changing the temperature. However, we don't really want to use temperature since it isn't the full energy of the gas, because it's the average kinetic energy of all the particles. What we really want is something called internal energy, which I'll represent with this little capital U here. This is a sum of all the kinetic energies of each of the particles. So let's just focus on one particle here and generalize it to all of them. And to make it even simpler, let's only focus on one axis of movement. So what is the force that only one particle exerts on the wall? Well, force is just the change in momentum over the change in time. So when a particle hits the wall, its velocity changes completely, from v to negative v. This means the change in momentum is equal to 2mv. So the average force on the wall is equal to 2mv divided by delta t. But since displacement is just velocity times time, we can see that the time between each collision of the wall is equal to the distance the particle travels over the velocity of the particle. The distance of the particle travels is 2x, where x is the length of the box. So the time is 2x divided by v, and with a little simplification, we can see that the average force is equal to mv squared divided by x. Now, if we want to find the pressure given by one particle, we can divide by the area of the wall, which is y times z, the height and the width respectively. You should note that the pressure on one wall is pretty much this pressure over the entire surface. Try to verify this for yourself. Anyways, this xyz in the denominator seems pretty familiar because it is. It's just the volume, so let's replace it with the v. Okay, so now we know the pressure that's exerted by one particle. So let's find out how much pressure is exerted with more than one particle. To do this, we can just add together the pressures of each particle. On the top, we get the sum of multiple v squared terms. So let's make an average, which I'll denote by this bar on top of the v, which is equal to all of these terms divided by the number of particles, n. So, we can rewrite the sum for all particles by multiplying by n. Okay, now let's account for multiple dimensions. By going through the same logic we did previously, the equations for the other dimensions are practically the same. So let's add them all together. Now, using the Pythagorean theorem, we can simplify the numerator and set it equal to the total mean velocity squared. And now, this is almost our equation for internal energy. And to fix that, we just need to divide by 2 on both sides. And now, we get that internal energy is equal to 3/2 times PV. Now, we need to find out what the work is. But what even is work? Well, work is supposed to be force times displacement. However, this only works if the force is constant throughout the displacement. So what if we got a force displacement graph like this? Well, then work is the area under the curve, which can be approximated as the sum of smaller and smaller rectangles of area f times delta x. This long s sign, also known as an integral, is supposed to represent the sum, or what it approximates to, the area under the curve. So, how can we find this in terms of pressure and volume? Well, pressure is just force divided by area, and volume is just area times displacement, so area cancels out, and what we're left with is just force times displacement, or work. This means we can write this as an integral, the area under the curve, of a pressure-volume graph, instead of a force displacement graph. This is pretty hard to visualize, so we can create something called a phase space. For every pair of numbers, coordinates in the phase space, there's a corresponding physical state in the system. This phase space specifically is pressure over volume, and the state of the system will be represented by a physical model in the top left. Now, a curve in the phase space corresponds to a thermodynamical process, and the work done by this process is just the area under the curve. For all you calculus students out there, this is probably really easy to compute. But for others, it's not, so we have to use approximations. So now, if we know what the work is, and what the internal energy is, we can use it to find the heating, or Q. However, there's a quick caveat about the work I want to talk about. The work that's the area under the curve left to right is the work done by the gas, on the piston. However, if we want to find the work done on the gas, we have to take the negative of the area under the curve left to right. Because of Newton's third law, the forces are opposite but equal. So here's a quick example. If the process is done from A to B, the work done on the gas is negative, but the work done by the gas is positive and can be computed by the area of this rectangle. However, if the process is from B to A, the work done on the gas is positive, but the work done by the gas is negative. This convention changes how we write the energy conservation law. One is delta U is equal to Q plus W, where W is the work done on the gas, and the second one is delta U is equal to Q minus W, where W is equal to the work by the gas. Another useful tip to know is that if the volume decreases, the work done on the gas is positive, but if the volume increases, the work done by the gas is positive. In the next video, we're going to be going over how gas engines work and the laws of entropy, which enable these to work.